Hey guys, Miss Marusik here, and in this video we're going to be talking about answering free response questions having to do with solutions and intermolecular forces, as well as looking at some separation techniques that I could use for solutions, which is a topic that often pops up in some of these FRQ questions. So to start us off here, we have the structures of pyridine and benzene given to us, and it asks us to identify all of the types of intermolecular attractive forces that could exist between the solute and solvent for these particular mixtures here. So they give us pyridine and water. So the first thing I did is I went and identified the individual types of IMFs. I see that pyridine is polar, and so its dominant type would be dipole-dipole. Water, as we know, has hydrogen bonding. So when I combine these together, water does not maintain that hydrogen bonding since pyridine can't contribute to that attraction. And so therefore we would say we had dipole-dipole forces, but we also would have London dispersion forces because remember, we always have that type. Now, with benzene and water, benzene has London dispersion forces as its dominant type because it's nonpolar. And so both of these kind of get an adjustment in their name. Obviously, water cannot maintain hydrogen bonding with the benzene, but it will keep its dipole moment present. However, the London dispersion, we don't keep that part of the name. Instead, we call that induced dipole. The permanent dipole moment on the water will induce the dipole on the benzene. However, even though we have that type, we would also have London dispersion forces present as well. So now that I have my types identified, it asks which substance, pyridine or benzene, should have a greater solubility in water. Well, don't forget, the stronger the attractions that I form, the more likely soluble we are. Also, if I think about what forces I had to begin with and what forces I'm forming, I think we'll see why the pyridine is more soluble in water than the benzene. Remember, the pyridine has fairly strong dipole-dipole and hydrogen bonding, and we're trading that out for a fairly strong dipole-dipole force. Those forces of attraction are similar in strength. The ones I had before are similar in strength to the forces I had afterwards. However, on benzene and water, I had a weak and fairly strong attraction, then now I would be trading out for something that's fairly weak. So the hydrogen bonding is not likely to break apart to go and force a much weaker dipole-induced dipole forces. So more than likely, this combination would be practically insoluble with each other, if not completely insoluble with each other. So to justify that in the next example, it says, hey, the dipole-dipole forces in a pyridine and water mixture are stronger than the dipole-induced dipole forces in a benzene and water mixture. So what that would mean is that pyridine and water would be the more soluble combination. Now this last question on this part asks, hey, I have a molecule of pyridine. Draw how a water molecule would interact with the pyridine using a dashed line to indicate the strongest type of intermolecular forces. So what I did first is I tried to go and identify a partially positive, partially negative end on this pyridine. Now, a little bit easier said than done. The carbons and hydrogens tend to all cancel each other out over here. That end of the molecule is pretty nonpolar. However, the nitrogen end of this, nitrogen is much more electronegative than carbon, and so that would cause a pull toward the nitrogen, and so my overall dipole moment would mean that this end of the molecule will be partially negative. Now what that probably means is this other end is partially positive, but if that's not as clear, as long as you've identified that one end as being partially negative, I can now go and attract water to that end of the molecule. And so that's what I did. I attracted the partially positive of the hydrogen in water to that nitrogen using a dotted or dashed line to indicate an intermolecular force. All right, let's go ahead and look at the next page. Now the next page talks about ionic solubility and ion dipole attraction strength. As we already know, some ionic compounds are soluble in water while others are not. It really depends on the strength of the original ionic compound. If the original ionic compound was held together so strongly that the new ion dipole forces aren't strong enough to pull it apart, then we're going to end up being insoluble. We're going to remain as that original ionic compound. But if the new ion dipole forces are stronger than the original ionic or either similar in strength, then we are likely to go ahead and dissolve. So really depends on, is that new attraction to the water at least as strong or greater in strength than the ionic compound was to begin with. Now, let's say we have figured out that an ionic compound will indeed dissolve, that the ion dipole forces are strong enough to pull it apart. Once those attractions then form to the water, there's even differing strengths of those attractions as well. So that's what this question here addresses. It says, hey, I have some ionic compounds that have particular charges and particular radii. And it wants to know if these have dissolved, which of the cation is most likely to have the strongest interaction with an adjacent water molecule. Again, we're assuming that these have indeed dissolved, but we want to say which of these would be most strongly attracted to the water. When would that ion dipole attraction be the strongest? So this uses the idea of Coulomb's law. Remember, Coulomb's law is all about charge and distance. So when I'm trying to pick out which one of these might have stronger attractions, I would say, well, I know as magnitude of charge increases, that helps out attractions. So I would narrow that down then to magnesium and calcium because they have the bigger magnitude of charge. And then I would want to think about internuclear distance, the distance between this time the ion itself and the water. So I'm looking at that internuclear distance this time. And when I think about that, the radius would affect me there. Well, the bigger the radius, that would mean weaker forces. The shorter the radius is, that would mean stronger forces. So I picked the magnesium +2. Again, it had the largest magnitude of charge, but it also had the smallest radius, which would give us a really short internuclear distance, and so therefore we would get stronger attractive forces there. On the flip side, if I was trying to pick out which one had the weakest interactions, I would have guessed the potassium. Not only did it have the smallest magnitude of charge, but in having the biggest radius, it would also have a large internuclear distance, and so therefore we would get those weak attractive forces. So kind of a concluding statement about that, basically, as the magnitude of charge increases, or as the internuclear distance decreases due to that decreased ionic radius, that would get a stronger strength of attraction to water molecules when I'm dealing with ion dipole forces. So then in this last piece of this example here, it says draw a picture of how water would interact with the ion you selected to have the strongest interaction with the water. We had magnesium +2 as the strongest one, and so then I would just draw those waters interacting around it. Again, the partially negative of the oxygen in the water molecule would attract to the positive magnesium there. So just like we did last class. All right, the last example on this page talks about picking a reason that could explain why silver chloride is insoluble in water. And so I'm going to kind of roll through these options here. Remember, if I'm insoluble, that must mean that something is stronger to begin with than whatever new attractions I'm forming, which is why we stay together as the original thing. So kind of looking through my options here, the first one says the London dispersion forces between water molecules are very weak. Okay, while that may be true, water molecules have more than just London dispersion forces, right? They have dipole-dipole and hydrogen bonding in them. So they're not like very weak, okay? I mean, they're weaker than bonds a lot of times, but not super weak. And not only that, but this doesn't help to explain why the silver chloride is insoluble in water. So then I look at the next one. It says, hey, ion dipole forces between silver ions and water molecules are very strong. Okay, that might be true, but here's the issue. I'm trying to explain why silver chloride is insoluble in water, why it doesn't dissolve. And so what that means is I want to argue why the original attractions were stronger than the attractions to water. So B does not help me prove my point. So I keep on going here. The next one says, hey, the ionic bonds between silver and chloride ions is very strong. Well, hey, that sounds good. If those original ionic bonds are super strong, then that would mean it would take a lot of attraction to break them apart, which apparently I don't have here because the silver chloride is insoluble. So that's sounding really good here. The last one says the covalent bonds between hydrogen atoms and oxygen atoms are very strong. All right, let's be real here. That might be true, But in no shape, way, or form am I trying to break covalent bonds in this scenario. I'm trying to break ionic bonds in the silver chloride, but for the water, I'm trying to break IMFs. I'm not trying to break the covalent bonds apart. So D is kind of ignoring the fact that I want to argue why silver chloride is not dissolving in the water, and so that does not help me there. So that's why that answer is very clearly C. All right, so next, let's talk about some separation techniques I could use if I know I have some sort of solution. So first off, if I'm trying to evaporate a solid solute and a liquid solvent, evaporation can be used. This is a very uncontrolled evaporation, okay? Like I just have some sort of container, typically an evaporating dish, where I have my salt solution, for example, or I could even have something like a solid sugar dissolved in water. And what I would do is I would heat it up until the water evaporates off and leaves behind my solid component. Most of us are familiar with that process. However, if I'm trying to separate a liquid solute and liquid solvent, this process is not quite controlled enough for me to be able to capture those two liquids separate from each other. And so I need some other methods. And those two methods are going to be chromatography and distillation. Now, one quick thing before we talk about those two that I want to mention here, and that is that filtration can never be used to separate a homogeneous solution. Homogeneous solutions have really small particles in them, and the filter paper is just not big enough to pick up those pieces. It works for heterogeneous mixtures, but not for homogeneous mixtures. So be really careful on that because that can be kind of tricky. All right, so let's talk about chromatography. Chromatography is a method of separating mixtures based off of differences in intermolecular forces, okay? Usually on a chromatography experiment, you have a stationary phase, some sort of solid which allows substances to move through it, but it itself stays in place. Okay. The mobile phase is something that passes through that stationary phase and it carries substances that need to be separated. Now, there's lots of different types of chromatography. A lot of you might remember from biology doing a gel electrophoresis. That is actually a version of chromatography. The one that's typically referenced in chemistry is what is called a paper chromatography, and we'll kind of talk about that here in a little bit. But on all types of chromatography, what will happen is that my mobile phase, my solvent, will naturally pass through that stationary phase. I don't have to do anything special to it a lot of times to get that to work. It just naturally travels through and will carry the components of my unknown solution with it. And depending on the interactions that those components have with both the mobile phase as well as with the stationary phase will depend on how far it travels on my chromatogram. So here's the deal. Less attraction to the stationary phase and more attraction to the mobile phase will mean that my component will travel along with that mobile phase. It's more attracted to it than to the phase that's staying in place. So if it's more attracted to what's moving, what that means is that component will travel further up your chromatogram, which the chromatogram is just your developed result of your chromatography experiment. However, if I have more attraction to the stationary phase, the non-moving component, and less attraction to the mobile phase, what's moving, then that means my component will not travel as far. Its attraction to that non-moving phase will help to hold it in place. Now, like I said, the most common type that we see in AP chemistry is what is referred to as a paper chromatography. Usually you'll have some sort of ink, dye, pigment kind of situation that we're wanting to separate out. And so what you do is you get a piece of filter paper and you place a dot of your pigment on it. And what you would do is mark with a pencil where that start point is, because eventually that pigment is going to end up separating and moving. So putting that pencil line there will help you to know where you started. And then what you'll do is you'll set it into your solvent. And your solvent will either be polar or non-polar. If it's polar, then it's probably more than likely more polar than the paper. If it's non-polar, then the paper is likely more polar at that point. So kind of keep that in mind, that we could switch out that solvent for something that's polar or something that's non-polar. It depends on the experiment. And what we'll do is we'll just barely set that paper into the solvent, and that will allow that solvent to start to rise up the paper. Now, eventually, it will reach a point where it gets close to the top, but you want to pull it out before it gets all the way to the top. Otherwise, it's going to mess up your results. And what you'll end up seeing is that the components of that pigment will end up separating themselves out. So we have both our origin line, the original pencil line, as well as our solvent front. Now, if we're closer to the solvent front, like this top one up here, what that means is that if the solvent was more polar than the paper, this piece would have been the most polar component out of the solution. Again, if the solvent is the mobile phase and traveling up and it is polar, then the polar component is going to be attracted to it, meaning the least polar would be down here at the bottom. However, if I flip that around, if the paper is more polar than the solvent, paper being the stationary phase, staying in place, then what that means is that the most polar component would stay in place, attracted to that non-moving paper. And so therefore this bottom marking down here would be the most polar component. So we really have to ask ourselves, what's more polar, the solvent or the paper? Because then that's going to depend where our most and least polar thing are in the experiment. Now, I'll be honest with you, when we give you pictures of this on an AP test, you're going to see like really ideal looking chromatograms here where the dots are pretty separate from each other. I would encourage you to watch this video clip right here that I've linked. It actually shows a chromatography experiment in real life. So you can see that those colors don't get separated quite so cleanly like that. You kind of get more of a blend, but you can still pick out where those different colors travel to for the different pigments. So if you want to see one in action, this is a great little video clip to watch. Now, one of the other things that I can calculate with this experiment is what is called an RF value, referred to as a retention factor value. Retention factors basically tell us how much is it traveling along with the solvent. So an RF value is the distance the spot traveled from the origin line over the distance the solvent traveled from the origin line. So basically, like, let's say for this middle dot here, it traveled about halfway up between the origin line and the solvent front. I might guess that that traveled maybe half of what it was supposed to, and so it would have an RF value of 0.5. For this bottom dot here, I might say that that only traveled maybe a fifth of the total distance here, and so that might have a retention factor of 0.2. Obviously, it's a little harder to ballpark them. It's a lot easier if you have actual data, because then you can calculate those values. By the way, if you were conducting a chromatography experiment where you had unknown parts and you were trying to identify those unknown parts, components that had similar RF values would indicate similar components. All right, go ahead and flip the page to the last one here. So here's an example. It says we had a marker that was containing an overall maroon colored ink, and it was analyzed in a chromatography experiment. So what they did is they would have originally had their maroon mark on this origin line, and then as they let the solvent travel through this, so our solvent would move on up, and as it moved on up to that solvent front, what would happen is it would carry the components of that pigment with it. So this apparently was made out of 3 components, blue, purple, and red. And so what it wants us to do is to answer the following questions about the chromatogram shown. So it says here, hey, in this experiment, water was used as the solvent. Well, think about what we know about water. We know water is super polar, right? So if it's super polar and that polar thing is moving along, it's asking, hey, which pigment was most attracted to the water? Well, if it's attracted to the water, it's going to move along with the water, and the component that moved along the most with this was the blue. And so what that means is that the blue component would have been the most polar of the components. Now the next question said, hey, a non-polar stationary phase was used in this experiment. So that means this chromatogram here was on some sort of component that was non-polar. So then it asks, which pigment was most attracted to this stationary phase? Well, again, if it's attracted to the thing that's not moving, then that component is also not going to move very far. So I would guess here that that would be the red pigment that I see here. Now, what that means about the red pigment is that this would have been the least polar component, since it was attracted to the non-polar stationary phase. Now, keep in mind that if I change those around, if the non-polar was the solvent and the chromatogram itself, that stationary phase, was polar, that would totally alter the results that I have here. So be very careful with analyzing where those attractions lie. By the way, it also says here, if a non-polar substance was used for the mobile phase instead of the water, and a polar stationary phase was used, how would you expect the chromatogram to change? So as we talked about, if I flip this around as far as what substance is where, if now my solvent moving is nonpolar, then that would mean this red nonpolar thing would move with it, and the polar blue would stay in place because it would be attracted to that stationary phase. So basically, you would see the results would be flipped. All right, last but not least down here, it asks us to calculate an RF value for the purple ink, which was right here. So again, an RF value compares how far that pigment traveled from the origin. I see it traveled 6 centimeters over the total distance traveled from the origin to the solvent front. So that would be from here to the solvent front is 10 centimeters. So that RF value is 0.6. Now, let's say you had some other markers that you knew contained similar pigments. If you were trying to match up another pigment to the purple pigment, if you wanted to say, do I have the same purple pigment in this other one? If it has the same RF value, there's a really good chance that those two purple pigments might be the same pigment. So keep that in mind. Again, similar RF values would indicate that I have similar components in our mixtures. All right, last but not least down here, we have distillation. Distillation is a method of separating mixtures based on different boiling points. This is a very controlled setup for evaporation. Basically, I would have down here my solution of 2 different liquids that had different boiling points to them. One of the boiling points would be lower, indicating weaker intermolecular forces. And what would happen is that lower boiling point substance would boil off first. As I heat this up, I would reach that lower boiling point before I reach the higher one. And so that lower boiling point liquid would boil off. However, I have a stopper up here. And so what would happen is I would run that gas through what is called a condenser tube. A condenser tube is kind of like a double layered tube where the inner tube is where I run through the gas, and the outer tube I would actually run water through it. Cool water that would help to cool down that gas and cause it to recondense into a liquid. And so then I could collect that liquid, and when I do that, it is called the distillate. So based on having different intermolecular force strengths, I can predict which one might be in that distillate first and which one would remain in the original distilling flask. So it says here, hey, I have a solution between formaldehyde and water that was separated using a distillation process. And it asks which of the 2 substances would be present in the distillate first and why. And again, the distillate is what's getting boiled off first. So what I would want to do is ask myself, well, which of these would I predict has the lower boiling point? Well, formaldehyde pictured over here is polar and would have dipole-dipole, but it does not have hydrogen bonding in it because I don't have the hydrogen directly attached to that oxygen. However, water, as we know, does have hydrogen bonding. So if I was to predict which of these has weaker forces, I would guess the formaldehyde, which means I would guess the formaldehyde to have a lower boiling point, and so therefore it would boil off first. And if it boils off first, then I would condense it into the distillate first. Now, eventually, if I continue to heat it, I could eventually get the water to boil off as well. The problem with that is that once that evaporates off, then I end up with both liquids back in that distillate, and that doesn't help me because now my solutions are back together, whereas I wanted that solution apart. So you got to be sure that you're kind of pausing the experiment after the first one has boiled off, but before the second liquid boils off. All right, now this last question here is kind of a throwback to what we talked about earlier in the notes. It says, identify all the types of intermolecular attractive forces that could exist between formaldehyde and water when it's that solution, and those would be the forces that would be broken during the distillation process. So looking here, I know formaldehyde had dipole-dipole, water had hydrogen bonding. However, water cannot maintain that hydrogen bonding with the formaldehyde, and so therefore I would just call that dipole-dipole forces. However, as we have already said, I would also always include London dispersion forces as well. All right, hopefully you're feeling good about answering free response questions, and we've gotten at least a little bit familiar with the process of chromatography and of distillation. If you have any questions or need any help, please feel free to email me. Bye, guys.